Dear students, welcome to ECA1 lecture. The topic of today's discussion is superposition theorem. Superposition theorem basically used for analyzing the network that have two or more sources that are not in series or parallel. It reveals the effect of each source on a particular quantity of interest. For the sources of different type, which affect the parameters of the network in a different manner, and apply a separate analysis for each type with the total result simply the algebraic sum of the result. So we can define the superposition theorem as the current through or voltage across any element of a network is equal to the algebraic sum of the current or voltage produced independently by each source. Since the effect of each source will be determined independently, the number of network to be analyzed will equal to the number of sources. It means that if we have two or more than two sources in the network, so we have to analyze our whole network equal to the number of sources. For example, if we have two sources in the network, we have to analyze our network two times. If we have three sources in our network, we have to analyze our network three times. Superposition theorem is not applicable to the power level. In our case, in our example, we will see that the superposition theorem is not applicable to power levels. If we have multiple sources in our network, we have to take one source at a time and remove the other sources. When removing a voltage source from a network schematic, replace it with a direct connection, or we say that with a short circuit of 0 ohms. Any internal resistance associated with the source must remain in the network. From the figure you will see that if we are going to remove this voltage source, we have to replace it with the short circuit, but the internal resistance of that source remain on its position. Now if when we are removing a current source from a network replaced by an open circuit of infinite ohms, any internal resistance associated with the source must remain in the network. From the figure you will see that we have that current source I. When we are going to remove that current source, we replace this current source with an open circuit, but the internal resistance remain on its position. In order to understand the superposition theorem, let us solve an example. In this example, we have to find the current through the resistor R2 and also demonstrate the superposition theorem is not applicable to the power level. So we have to find the value of I2 which is flowing from the resistor R2 because of that source and that source, so voltage source and the current source, using superposition theorem. In the first step, we have to take only one source. So we take a voltage source and remove the current source. We remove the current source by replacing it by an open circuit. Now from the figure you will see that when we remove the current source from the network, it becomes a simple series circuit. So the current through IR2 is basically I prime by I prime 2. I prime 2 stands for it is because of the first source. So the value of the current is basically equal to E by RT. E is the total voltage, RT is the total resistance of that circuit. So E is I2 prime is equal to E divided by R1 plus R2. When we substitute the values of R1, R2 and E, we will get 36 volt is basically value of E, 12 is the value of R1 and 6 ohm is the value of R2. We will get the value of I2 prime which is equal to 2 ampere, and you will see from the figure that this 2 ampere current is flowing down in downward direction. Now in the second step, we take a current source and remove the voltage source, and when we are going to remove the voltage source, we replace it with the short circuit. Now you see from the figure that R2 and R1 are in parallel, and I2 double prime is the current flowing from R2 because of that current source. So when we apply current divider rule here, we will get I2 double prime is equal to R1 into total current divided by total resistance of the circuit. when we substitute the value of R1, R2 and I, we will get I2 double prime is equal to 6 ampere. Now from the figure you will see that this I2 double prime is flowing in the downward direction. So both the currents are flowing in the downward direction. Using these two figures, we will see that I2 is basically I2 prime plus I2 double prime, because due to that voltage source I2 prime current is flowing in downward direction. Due to that current source I2 double prime current is also flowing in downward direction. So the direction of both the current is same, so the net current is equal to I2 prime plus I2 double prime. The value of I2 prime is 2 ampere and I2 double prime is 6 ampere. So the total current I2 flowing from resistor R2 is basically equals to 8 amperes. Now, solving for the second part of the question, power levels. From the figure you will see that the I2 current is flowing in the downward direction, which is equal to 2 ampere. So the power is equal to I2 prime square into R2, which is equal to 24 watts. Now when we take a current source, you will see that the current flowing I2 double prime in the downward direction is basically equals to 6 ampere. So when we substitute the values in the power relation, we will get the value 216 watt. So the net power because of these two currents is equal to 240 watts. P1 plus P2, P1 is equal to 24 watt and P2 is equal to 216 watt. The total power is equal to 240 watts. Now using the superposition theorem, we see that the current flowing from R2 is equal to 8 ampere because of the both sources. So when we calculate the power using 8 ampere current, you will see that the total power is equal to 380 watts. Now we see that due to the power due to the individual sources is equal to 240 watts, but the total power dissipated by this resistor is equal to 348 watt. So it means that the power the superposition theorem is not applicable to the power levels, because the individual power, the sum of the individual power is not equal to the total power. That's all. If you have any question, please drop your question in comment box. Thank you very much.